This is the third video of our climate and tree growth relationship project. And so in previous videos I showed you how to obtain tree ring measurements from the ITRDB and how to verify the accuracy of the cross dating, so the matching measurement series from one tree to another using COFECHA. Now in this video, this is part one of two in the third video, where I'm going to show you how we then take all of those measurements, so those multiple trees, and how do we condense them down into one tree ring chronology, so one wiggly line instead of a bunch of wiggly lines. And we're going to do this using the DPLR package in the R programming language. In this video I'm going to show you how to download and install R, how to get that DPLR package up and running, and then in the next video I'll show you how we actually do the analysis. So what we're doing when we detrend and standardize tree rings is we're removing growth trends that aren't due to that common signal, that common climate response of trees. So if we look in this figure over here in the upper right, we see that this is a wiggly line, right? So what we have on the x-axis is years, right? So over time. And what we have on the y-axis is the ring width in millimeters, right? So some years are going to be wider and some years are going to be narrower, and you generate this wiggly line, right? Dendrochronologists generate wiggly lines. Just like cows produce milk and ice cream factories produce ice cream, dendrochronologists produce wiggly lines. So here's a wiggly line. This is one tree, right? So one core that was measured. And what we see is that the measurement, there's a trend to the series, right? So this is a time series and there's a trend. We have there's variability, right? The wiggly line goes up and down. But in general, we have this decreasing ring width from somewhere, around 2 millimeters down to around 1 millimeter. And that trend comes from the fact that as a tree gets older and bigger, it's got to put more biomass around a larger surface area, right? So even if the tree is growing the same amount, when it's small, that'll be a wide ring, and when it's bigger, that'll be a narrower ring. So that has nothing at all to do with climate. That just has to do with the fact that the tree is getting bigger as it gets older. So if we have multiple trees of different ages, so we see over here on the left, here's a tree. If we're looking at the same year, in this tree, it's sort of, middle age growth ring, and the same thing. But this tree is much older, but we're looking at the same year. And here this tree is much younger, and we're looking at the same year, and here, and so on. So if we were to just take an average of the ring width in millimeters, it's going to be meaningless, because we'd be, in some years we're measuring an old age ring, and in some trees we're measuring a young age ring. So we have to be able to compare them across time, accounting for this age-related growth trend. So what we do is we call that detrending. We have to remove this growth trend and other sorts of non-climatic things. So for instance, in this one, we can see that age-related growth trend, which is usually a negative exponential function. Then we see something going on here. This is a growth release. So this tree, the growth was slowing down, and then maybe a neighboring tree died, and this tree was able to grow a little bit more, and then as the canopy filled in, it slowed down again, right? So there's these weird things that are not related to climate, and so we have to remove those trends. So how do we do that? What we do is we fit a function to the ring width series, and then we create what's called an index, a ring width index. So for instance, in the top panel here, we see here's a tree that has that age-related growth trend. It's a negative exponential curve that we can fit to that series. Here we have a tree in a closed canopy forest. So the closed canopy, and we see a growth release, and then we see that age-related trend kicking in. So, again, maybe the tree is growing under a canopy, and then a neighboring tree dies, so it has a release, and those rings get wider, but then as the tree gets older, we have that trend. And then sometimes it's more of a straight line function, right? So the way we do this is we calculate an index. So we fit a curve, so you can fit a function to the ring width measurements, right, that sort of approximates that trend. You can summarize that with an equation. So in this case, we have a negative exponential equation here, the negative exponent. And so we fit that to the series, and then we take the residuals. So we fit the trend and we look at, okay, is an individual point higher or lower than the predicted value from that growth trend? And so then what we have is an index, right? We're no longer looking at millimeters. We're looking at an index with a mean of 1, and years that are wide are going to be larger than 1, and years that are narrow are going to be less than 1. Then we can take all the index values from each core and we can average those together, and then we'll have a meaningful index, regardless of how old the tree is at any given year. Here's how we do that. So we have a ring width series, so the black line is our wiggly line of ring widths in millimeters. Then we fit a trend line to it, so in this case it's a straight line, that's the red line here. So for any given year, we have an actual value and we have a predicted value. So the predicted value is just what's predicted by our model. So all we do to calculate the index is it's just the actual value divided by the predicted. So if the actual value and the predicted are the same, you would get a value of 1.0, because the same number divided by itself is 1. If the actual value is wide, the ring is wider, then you'll have a value greater than 1. If the actual value is lower than the predicted, you'll have a value less than 1. So that's all we're doing for detrending, and we're going to do it in R. So to download R, all you do is fire up your internet browser, and in your Google search box just type the letter R. And you'll come to the top link will be the R project for statistical computing. So all you do is find this link that says download R and click that. You'll have to choose a mirror site. So this is where are you going to download it from. So these are places all around the world. Just pick something in the US and it'll be faster. So you can pick, I don't know, I'm going to take this one at University of California at Berkeley. And then you just download the version of R that works for you. So if you're running a Linux machine, download the Linux one. If you're running a Mac, download the Mac one. And if you're running a Windows one, download the Windows one. Download the program, run the installer, and you're good to go. I'll show you since I have it loaded up already. I'll just open it up, and this is what you see. So R is a program and an environment for programming and for statistics. It's got a little bit of a learning curve because you have to type in commands, but R can do a lot of stuff. So we can see right here, I can type in, R can do math, so I put in 2 plus 2 and hit enter, and we get 4, right? R can also, you can program variables in here. So if I make a variable called x, and I use this sign, the less than and the dash, and that combination of signs is called the assignment operator. So what I'm saying is I'm creating a variable called x, and in it I'm going to assign some properties. So let's say I'm going to say x equals 2 plus 2, right? Then I can type x, and R knows that the value of x is 4, right? So it's some very simple computing that you can do, but R can do a lot more complicated stuff too. Okay, so the one thing you're going to need to do is you're going to need to download some packages to do our tree ring analysis. So these are little add-ons that have little routines of code that do stuff for us. So I'm going to download, so you go into packages and you go to install packages. Again, pick a mirror site to download from, so anything in the US is fine. I'll go with that Berkeley site again. And you're going to download 2 different packages for this project. So the first one you're going to need is DPLR, and that stands for Dendrochronology Program Library. So you can scroll down this list of packages down to D, and I'm going to look for DPLR. Here it is right here. So you click that and click OK, and R will download and install the package and all the stuff you need to go along with that package. This might take a few minutes, but then it'll be done. Okay, so there it is. It's downloaded and it's on my computer. The next one you're going to need to install is called tree climb, and that's the series of statistics we're going to run to look at the relationship between climate and tree growth. So I'm going to scroll down here to the T's, and I'm going to look for tree climb. Right here, tree climb. Okay, and I'm going to click OK, and it's going to go through and it's going to install it there, and we're all done. Okay, so do that, and then in the next video I'll show you how we run DPLR to detrend our series and make one tree ring chronology of index values rather than just millimeter ring widths.